And here we are again. So now we're going to look at electron configuration. So we've looked at how energy can be absorbed and emitted by atoms and how that gives us an idea of energy levels. Now we're going to take that a little bit further from the Bohr model and start to look at electron configurations and start to bring in some of the ideas that were brought in by quantum mechanics and our most recent, I guess, idea of how the atom is structured. So the electron configuration is the same definition as what you should be familiar with. It's the arrangement of electrons in order of energy levels in an atom. Okay, this is critical for us as chemists because the properties and the chemical reactions that elements undergo depend on the electron arrangement. So all noble gases are highly unreactive because they have a stable electron configuration, and all the noble gases in group 18 share that feature. They have 8 electrons in their valence shell. Okay, so in particular what we're interested in is being able to determine the outer shell electrons or valence electrons, because this gives us a lot of information on how atoms will behave in terms of the type of bonding, ionic or covalent, that they will form, how many electrons they will take on to form negative ions, or how many electrons they will lose to form positive ions, therefore allowing us to work out what charge they will be in ionic substances as well. So it is important to remember that electrons in the same shell have roughly the same energy, okay, and they're about the same distance from the nucleus. So we're grouping electrons into energy levels and distance from the nucleus in order to be able to start determining how they behave. So you will hopefully remember that the rule for the maximum number of electrons in an atom is 2n squared. Okay, so this being that n being our principal quantum number or shell number. Okay, so principal quantum number or shell number, and that if we are in shell 3 then 2n squared will be 2 times 3 squared. 3 squared being 9 will mean we can have 18 electrons in our valence shell. If we're in shell 4, then we can have 32 electrons in our valence shell, and so forth. So the shells are numbered 1, 2, 3 outwards from the nucleus, and this determines the maximum number of electrons that each shell can hold. So shell 1, 2 electrons, shell 2, 8 electrons, which is 2 times 2 squared, and so forth. So when we fill electron shells, we have to do them in a specific order. Generally, we fill them from lowest energy to highest energy from the nucleus out, because it increases in energy as we move away from the nucleus. Each energy level needs to be completely filled before the electron goes into the next energy level, though we do see some variations in that as we move on. And if you remember, when we go to 20, we do 4, 8, 8, 2, which you may be thinking, hang on a second, if 3 can hold 18, we put 2 in the fourth before we go beyond 8. Our valence shell can't hold more than 8. So if our third shell is our valence shell, it can't hold more than 8. In this case, once we put 2 into our fourth shell, we come back and fill the third, and we'll talk about that a little bit more. So if we look at sodium, you may remember that we put 2 into the first shell because the first shell can hold 2 times 1 squared, okay, which is going to be 2 electrons. Once that is full, we move on to the second shell, which can hold 2 times 2 squared, which is going to be equal to 8. Once we've filled that, we start filling the next shell, so we put 1 in the shell after. And we continue to do this all the way up to, for us, element 36 is the last electron configuration we need to be able to do. So one of the ways that we know that electrons are arranged in this way around the atom is because of a property called ionization energy. So this is a definition that you need to be able to essentially give by rote. So make sure that you put this into your notes and make sure it's specific. So the ionization energy of an element is defined as the minimum amount of energy needed to remove an electron from an atom or ion in the gaseous state. So it needs to be in the gaseous state first, so that the energy that we measure is the difference between it simply having an electron and not. So then we measure the amount of energy required to rip an electron off that atom. And what we see when we do that is that as we progressively remove electrons, the energy required to do so becomes greater because the pull of the nucleus is holding on to those electrons more and more. So as we remove the first electron, its ionization energy is quite low. So this one is for sodium. And then we can see we have this big jump here. So there's a big difference in energy, which means we have transitioned to another shell. Okay, because if it was in the same shell, then it would be a similar energy here. So as we can see here, so for sodium, which if you remember is 281, we remove the first one and then we jump into the next shell, so there's a big difference in energy. We then remove the 8 electrons from the second shell, which require just a little bit more energy each to be removed. Then you can see here, we then, after we've removed those 8, jump in energy again and remove the last 2 electrons here. So as you can see, this gives us evidence for that shell model that electrons are grouped in these energy levels. So when we do this, if we look at the energy of ionization, we can see that the outermost electrons are relatively easily removed, and then more energy is needed for the next, and then for the final 2 it's even more. So we can look at these kind of diagrams and predict what atom we're looking at by the number of electrons that were removed and the shell structures. Okay, and what it does is provide evidence, experimental evidence, that the theoretical idea of shells has some basis in our observations. What it didn't do was explain everything though. Okay, so as with many models, they don't always incorporate all the experimental data that we did. And what we found, or scientists found, was that there seemed to be some variation in electrons. So the current model of the arrangement of electrons is a little bit different to Bohr. So this is where Schrödinger and Heisenberg and the beginnings of quantum mechanics and wave mechanics started to inform our understanding of the atom. So what this did is discovered that electrons can behave both as waves and particles, and there's no definite orbit. So instead they inhabit a region of space. So they inhabit a specific region of space that we refer to as orbitals, but these orbitals contain electrons in sort of like a fuzzy cloud of probability. Electrons can pop in and pop out. And they're more charged clouds, so clouds of negative distribution because the electrons are negative. So what this meant is that we needed to adapt the model, and what we now have is we have shells being the largest energy level. Within shells we have subshells which account for the slight variations in energy we see within a shell, and in each subshell have a specific number of orbitals. And then an orbital can only hold a maximum of 2 electrons. So what we did was refined the structure into these higher levels of order. So shells are the major energy levels, which you could consider as your suburb if we were thinking about an address. Subshells would then be the street that you live on, so they're the next level of classification in, and then an orbital would be the actual house. Okay, so each time we're defining more and more the energy in a more precise way that the electrons are existing in. So subshells must be given a specific order, just like shells, where shells go from 1, 2, 3 out from the nucleus in increasing energy. Subshells are given labels of S, P, D, F, and G. And again, as we list them, this is increasing energy. So S is the lowest energy subshell, P, D, F, and then G. You need to learn this order, and we fill electrons into each of these subshells in order. And then in the S subshell, there is S orbitals. In the P subshell, we have S and P. In the D subshell, we have S, P, and D orbitals. So we use the labels S, P, D, F for subshells, as well as the orbitals that are within these subshells, which is a little bit confusing, but hopefully you'll get used to it. So this means that we can now take our shell model and look at it in much more detail. So if we look at this one here, what we're seeing is that as we increase energy, we can map this out like rungs on a ladder, and electrons will go into the 1s, and then they will go into the 2s. 2p actually has 3 orbitals, as we will see, and we just keep filling all the way up, and we don't put electrons in the next level up until we've filled the one below. So let's look at the details of it. So the type of subshell, S, can have one orbital, which is an s orbital, and hold a maximum of 2 electrons. Because the first shell only has an s subshell, it will only hold 2 electrons. So you'll remember our electron configuration of 2. For the p subshell, when we get into shell 2, it has both s and p in shell 2, which means it can hold 2 electrons in the s orbital. There are 3 p orbitals that can hold 2 electrons each, which gives us another 6. So when we get to shell 2, we can now hold 8 electrons. As we move into shell 3, it gets s, p, and d orbitals. And now it has one s orbital, so it can hold 2 electrons, 3 p orbitals, the same as the second shell had, so it holds 8 electrons, and now it has 5 d orbitals available, so it can hold a maximum of 10 electrons. This will take a little while to get used to, but as we practice it, it'll become very clear. Just make sure you have the number of orbitals in each shell and subshells and 2 electrons in each orbital noted in your notes. So what this means is, because electrons are waves, it also generates a particular shell of the orbital. We'll look at this in more detail as we continue our studies, but it is at this stage for SL important for you to remember that the orbitals have particular shapes. The shape of the s orbital is a sphere. The shape of the p orbitals is sort of like an infinity symbol. It's a dumbbell shape with 2 lobes, and we get, because there's 3 p orbitals, we get one that lies across the x-axis in 3-dimensional space, and we refer to this as the px orbital. We have one that lies across the y-axis in 3-dimensional space, which is the py, and one that lies across the z-axis, the vertical axis, in 3-dimensional space, and we call this the pz. And so this, you can imagine arranged around the center of an atom, puts them around all areas in 3-dimensional space. Okay, a little bit more theory. So the Pauli principle is essentially the idea that states that an atomic orbital can only hold 2 electrons. Okay, so it can have 0, 1, or 2 as its possibilities, and these are the only mathematical solutions that are available for this model. Okay, so we can only have 2 electrons per orbital. This is because in the orbitals, electrons can either have what we call a spin up or a spin down orientation. So no 2 things can be in exactly the same place and at exactly the same time, but because they have opposing spins, there's 2 possibilities. This is like when you solve a quadratic equation, and you can have 2 answers where you get plus or minus a perhaps being the answer. So in this case, we can have a plus electron, which would be spin up, and a minus electron, which would be spin down in an orbital, and they're the only 2 solutions that we can possibly have. So this is a table that gives each of the subshells and introduces the way in which we put these arrangements in. So you remember with sodium we said it was 2, 8, 1. Now with subshell notation, we put the principal quantum number, which is shell 1, has an s subshell, and in this case would hold 2 electrons. Now we move into the second shell. First subshell is s, it will hold 2. Second subshell is p, and it will hold 6. So now I've got my 8 electrons, 6, 7, 8, 9, 10. So then I need to go into the third shell, the first subshell in the third shell is S, and I put my last electron 1 in here, and now I've run out of electrons. So these 2 went into my first shell, these 8 correspond to my second shell, and then this one went into my third shell. So we continue to do that for all our electrons, irrespective of the element that we're looking at. So we fill in this order here, so this diagram here, 1s into 2s, 2p, 3s, 3p, and then this one here, 4s, we'll talk about in our next video. But up until 18, we just fill in this order. So if we were doing chlorine, it would be 1s2, that's 2 electrons, 2, can't draw. Then we would go to 2s2, 2p6, so now I'm at 10. Still got to go, so because chlorine is 17, so I've got 10, I'm going to go 3s2, that's 12, and then 3p5 will put me at 17 electrons. So this would be the subshell notation for chlorine. Okay, whereas we would have previously written 2, 8, 7, this now is the way that we need to write it for subshell notation.